Hello everybody, welcome to this series of lectures titled VLSI design using LT Spice. So here we are going to learn about various VLSI design concepts using CMOS transistors in a software which is LT Spice. So there are going to be 6 different lessons. The first lesson which we are going to cover today is introduction to CMOS design. So after the theory part is covered, I will demonstrate how to import TSMC 180 nanometer technology file into LT Spice, and then we will do some simulations and try to characterize the NMOS and PMOS design transistors. Okay. Later on in the lesson 2, what we are going to do is we are going to learn about inverter design and characterization. Now after that, as a take home assignment, you will be able to design an voltage controlled oscillator of your own. So I will give you certain hints. From there you will be able to build up the further circuit. In session 3, I am going to discuss about static CMOS design and demonstrate full adder design, and then as a home assignment you should be able to design an SR latch. And session 4, I am going to cover dynamic CMOS design and demonstrate dynamic full adder design. Then as a take home assignment you will be able to design D flip-flop of your own. In the next lesson, session 5, we will discuss about pass transistor logic and design and full adder using pass transistor logic, and in your own free time you should be able to design multiplexer. Okay. And the last lesson would be a design of a memory design, that is we will design a 60 SRAM, and then you can build upon that concepts and design 40 70 SRAMs and DRAMs of your own. Okay. So let's in today's class we'll just get introduced to the concept of CMOS design. Okay. So if you see CMOS, which stands for complementary MOSFETs, the original idea of an FET was floated in 1925, and in 1935 a structure which closely resembled MOSFET was proposed. In 1960 the MOSFET actually started production. Okay. MOSFET means by 1963 you had an NMOSFET and PMOS, and both being fabricated together in a chip, and that is where this name comes in CMOS. Okay. Now till then, before 1963 you just had BJT, like bipolar junction transistors based circuits and processors. The major drawback was power. While all those circuits consumed power in the order of microwatts and above, the CMOS circuits consumed only nanowatts of power. So it was like 2 to 3 almost 3 orders lesser the power than the corresponding BJT circuit. So that was a great advantage. So that is why this jump from BJT to CMOS. Now if you see in 1993, okay, from 63 we had and in 63 when it started, so the CMOS devices were of few micrometer feature size. That means the channel length was in micrometers. So by the time in 1993 we had Pentium processor coming in, which had around 800 nanometers. So we started off from micrometers and we started coming below micrometer in the nanometer range. Okay, so 800 nanometer was the channel length. Okay, so when we say 800 nanometer or 0.8 micrometer technology, it means the channel length is 800 meter. So that is the minimum feature size which this technology offers. Okay. And the size of the core processor, Intel processor, was 16.7 mm by 17.6 mm. Okay, there were few thousands of transistors in this Pentium. And then today we have Intel 14 nanometer and AMD 7 nanometer processors. Okay. Now, so it is not that the CMOS technology has remained same. Okay, the basic principle of operation has remained same, but the device size has shrunk from few micrometers. Now it is almost come to single digit nanometer device size. Okay, it's not only that the device So that has enabled billions of transistors to be fabricated within a single chip. So in a single chip now you have billions of transistors, and not only the feature size has gone down, but the complex routing algorithms, multi metal layers, all those things have come, which has enabled close packing of the like if you have a single metal layer, so the routing becomes difficult. Now in the latest chips you have around 10 to 13 layers of metal, each separated by an insulating layer, and then you have wires which can interconnect these metals. So you see the routing has become now very compact. So that and then along with the transistor size being reduced, this multi-layer has reduced the routing requirement. So hence this chip has the total number of transistors which can be fabricated on a given die area has gone up highly, and also the frequency operation has gone high. That is because of several reasons. Okay, reducing the size of the transistors, that reduces the capacitances, okay, and so that there is an increase in frequency. Not only that, but several new architectures have come up. So at the algorithm level and at the architecture level also, several new concepts have been proved and adapted in the past many years, which has resulted in frequency operation in gigahertz. So now very complex computation can be undertaken by these microprocessors, today's microprocessors, unlike the previous ones. Okay, so let's also discuss some limitations of the CMOS technology. So this was the ITRS prediction, like by the time you come to 2020, the device size is going to be few nanometers. Okay, so you see here the gate length, the blue line, this is 50 nanometer, and then here it is coming to 7 nanometer. So this is almost the prediction has been, this was done in 2002, so this prediction is almost come true. Okay, there were a few other predictions also. One said the gate leakage will keep increasing. Okay, that is the red line which is shown here like this. The orange line which is going like this. Okay, that is because as the device you keep shrinking the devices, the gate oxide thickness also will has to be reduced. Now if you reduce the gate oxide thickness, there will be tunneling of electrons from the gate metal to the channel. So it was predicted that the gate oxide leakage will increase. Okay, but you see this red dotted line. Okay, the gate leakage has in fact reduced. That is because initially when this prediction was made, we were talking about silicon dioxide. Okay, so when we shrink the device, this layer also requires to be the thickness of the oxide layer also requires to be brought down. So instead of, now what we are doing is like instead of using an 1 nanometer thick silicon dioxide, I'm just giving an example, we can use an 4 nanometer high K dielectric. Okay, like HFO2. HFO2 has got a dielectric constant of 4 times that of silicon dioxide. So the electrical property of a 1 nanometer thickness silicon dioxide will be same as that of an 4 nanometer thickness HFO2. So that is the reason why by graduating from migrating from silicon dioxide to HFO2 and using higher thickness gate oxides while maintaining the electrical characteristics, because HFO2 has got a higher K dielectric, so we are able to control this leakage currents and gate leakage current. So that's why this line has actually not gone up and it is under control as of now. Okay, now there are a few other things which have actually increased. This green line represents the subthreshold leakage. Okay, so we'll see that in detail. The subthreshold leakage continues to be a problem area. So as the device size is shrinking, the subthreshold leakage is increasing. Okay, and also the dynamic power also is increasing. Okay, we'll see these two things. I'll cover it in detail in the next few slides. Okay, so this was another prediction. Like the Pentium itself, if you see the size of the Pentium is somewhere, okay, around 10 if you consider it as, it was around 10 watt per centimeter square. Okay, now if you consider an hot plate, which we generally have 10 into 10 centimeter hot square hot plate, okay, and it dissipates in 1000 watts of power. So you, even the hot plate will have that kind of heat, right? The power density will be 1000 watts of hot plate, okay, and the hot plate area is 10 into 10, so it will have around 10 watt per. So you can imagine the Pentium would be as hot as an hot plate, right? So it predicted that, and if we continue to put more and more transistors into small chip area, then the ICs will start getting red hot, and to the extent of getting as hot as a nuclear reactor or an rocket nozzle. So lot of work. So it has not actually gone up like this. So lot of things have been done to control the power dissipation in VLSI design. Okay, so after 2002, you will see that this has not, this graph, and we couldn't have allowed this going high, right? So lot of things have been done to reduce the power dissipation. That is what we are going to learn in the subsequent classes. But still the power dissipation has gone high, and that is the reason you see all these microprocessors right now come with lot of fan and accessories, whereas this was Pentium processor which never required. So so although power is under control by many techniques which we will learn subsequently, but still the power is on the higher side. So that we need to take care even now. Okay, now, so if you, in the digital circuits, the MOSFETs are generally used as an switch. So if you have an NMOSFET, if you don't give any gate voltage, so NMOSFET is just on the P substrate, you have two N regions, and then you call one as source and one as a drain, and then you give a gate voltage. Now if you see, no current can flow here. And why is that no current can flow? Because if you see, this is N, suppose I give a source as a ground and drain as a VDD, right? So this is become N, this becomes N. If you see, the equivalent is an two diodes interconnected like this. This is N, this channel is P. Okay, so that becomes a diode, and this is P, this is N. So again you have, so this particular diode which is formed between the drain and the channel, this is a diode that gets reverse biased when you give a positive voltage here. So there is no current. So there is one of these diodes, when you, if you don't have any gate voltage, when you give either you give plus here or you give plus here, doesn't matter, one of these diodes will always be reverse biased, and there is no current which will flow in this device. Okay, now for an if you want to switch on, then you can give an power supply to the gate also. So when you give a power supply to the gate, there will be some electrons available. It will first push all the positive carriers of the channel to the bottom, and then whatever free electrons are available because of thermal excitation, that will be pulled towards the gate, and hence a channel will be formed. Also the electrons will be pulled. If when you are giving a positive supply to the gate, electrons will be pulled from these two N regions also. So you have a channel formed as and when we give a positive gate voltage. So now this starts acting like an switch. Switch means switch on. It acts like an on condition switch, wherein now the current conduction can happen between the drain and the source. Okay, so ideally speaking, when you don't give any supply voltage, there should, the I off now should be 0. But practically when we see that, we will see that some picoamperes of current will flow in this. Now you will you should ask me, why are we so much bothered about picoamperes of current? It is because now it is not only picoamperes of current, but you have billions on billions of transistors which is there in a single chip. So if you multiply this pico by billions of transistors, then the current becomes if the total net current is going to be high, because each of these transistors, if they are going to have picoamperes current, and there are billions of these such transistors, then the total current becomes pretty high, and then that can result in heating of the chip, right? So that is why even this picoamperes current is we have to take care of that, and we have to find means and ways and means to reduce this also, right? So ideally R off should be infinity, but practically it is going to be when we see in the circuits, it's going to be in mega or gigaohms. Okay. Similarly, when I talk about this switch, it's not like a mechanical switch that you switch on and whatever voltage is available immediately will be available on the source side. Suppose you give on the drain VDD, the moment you put a gate voltage, that VDD will not be available in the source side. Okay, because what happens is the current which can flow in this device will be given by the ID equation of the MOSFET. So whatever is the maximum ID, only that much current can flow. And if there is a capacitor, generally you will find there will be a capacitor which will be connected onto the other terminal of the MOSFET. So that capacitor will slowly get charged through the ID which is flowing in this device. So it is not an you can't call this an ideal switch. So it will slowly that capacitor will get charged to it to VDD, and as the capacitor keeps getting charged at the output, okay, the VDS also keeps decreasing, right? Initially, suppose the source is 0 and you have given a drain as VDD, and then you are switching on this gate. So now some current starts flowing like this. Now the capacitance also gets charged. So you will find the voltage VDS is also decreasing. So the initially high current will flow, and that also not an infinite current. Current will be limited by the dimensions of this device, and then also as the output voltage rises, then also the current will start dropping because VDS is now increasing. So this transistor will come out of from the saturation region and it will start getting into the linear region. So these are all the practical things which you need to remember when you are designing. Okay, now this is what is again shown here. When there is no gate voltage, IDS is 0, but we said IDS won't be 0 because there will be some leakage current. And initially, like in this case, initially when obviously there is something known as a threshold voltage, right? This you might have studied in your device classes. So VGS has to be greater than the threshold voltage. So only then this will switch on. So whenever VGS is greater than the threshold voltage, the current will start flowing. So initially this is plus VDD and this is ground. So you will have VDS as VDD for a digital circuit. The moment you are switching it out, VDS will be VDD, and VG also will be VDD, because there is only going to be two types of power supplies in a digital circuit. So you are going to apply VDD here, and you are going to give the gate also VDD. Now VGS VDS is greater than VGS minus VT, that means this transistor is going to be in saturation region, and then the ID equation will be given by 1 by 2 mu n Cox W by L. So you see here in that condition also the current is limited by W by N and also by VGS minus VT square on all these things. So you see that not that infinite current will flow here. So the current will start flowing in this manner. Okay, and slowly as the voltage here picks up, then the current this transistor will come into the linear mode of operation. Okay, in the linear mode we know when VDS is lesser than VGS minus VT, then this is the equation which is applicable, right? So you need to understand that. Okay, so NMOSFET. Now MOSFET as a switch. Okay, so NMOSFET is we'll use only the NMOSFET generally to switch zeros, and we don't use it to transmit one. So the reason is explained here. Suppose this is a VDD out here. This is we are going to use NMOSFET as a switch out here. I am giving VDD here. Now I give so initially this capacitor is suppose is 0. Right now, if I switch it on this VDD, this capacitor has to get charged to VDD. So I am going to use this NMOS as a switch. So initially the capacitor is 0, and then I am putting a gate voltage, and I am switching on. So I am going to the gate voltage is going to be VDD. Okay, that's the logic 1 I am applying here. So logic 1 is available here. Now this output also has to go to logic 1 because I am closing the switch, right? So what happens? So you see there. Now if you see here, the current is going to flow from VDD towards CL. Okay, so when I say current, it means the positive charges, right? It is going to flow like this, right? Now for this MOSFET, this will be the drain, this will be the source. Why do I call this drain and source? Because for an NMOSFET, electron is the majority carrier for NMOSFET, right? So if the positive charges are flowing like this, okay, then the negative charges will flow in the opposite direction. So wherever the negative charges is coming from, that will be known as the source. So that is the reason this is source and this is drain. Now if you see here, as the output voltages keeps increasing, and it will reach V out, is when the V out here becomes VDD minus VTN, this transistor will get switched off. Okay, why? Because if you see here, when this reaches VDD minus VTN, what is VGS? VGS, here we are applying VDD, and this output voltage is VDD minus VTN, right? That means now between VGS, the potential between VGS is now VTN. So that is the threshold voltage at which the transistor switches on. Now if it goes beyond VTN, this transistor will be switched off, right? So the maximum voltage which will be available here is VDD minus VTN. So that is the problem when using NMOSFET as a switch to transmit a 1. But whereas it can transmit a 0 perfectly. Now suppose there is a capacitor out here, and it is already charged to 1 for some reason, because of from some other part of the circuit. Now I am going to use this switch to discharge that. That means I want to transmit a 0 from here to here. So I have an NMOS here. Now if I see here, this is 0. The moment I give an power supply A equal to VDD on to the gate voltage, okay, this gate source voltage will continue to remain VDD, right? Because this is 0, this is VDD. So irrespective of whatever is the drain voltage, this transistor will remain on. So until this will keep remaining on, and ultimately all the charge which was accumulated in the capacitor will get discharged to 0. So this can perfectly transmit a 0. Like so you have to remember that NMOS can perfectly can pass 0 perfect, but can pass a perfect 0 but not a 1. Okay, so whenever we are trying to transmit 1, so we don't use NMOS, we will use only PMOS to transmit 1, and whenever we have to transmit a 0, we are going to use an NMOS. Okay, so this is about an MOSFET, PMOSFETs. So in P MOSFETs, you see this is the P substrate on which in here what we started off. If I see, this is a P type substrate. Generally the substrates are of P type. You make two N regions, and then you put an oxide and a gate. So this becomes an N MOSFETs. Whereas here we have a P substrate. So to make a P MOSFET, first we have to make an N well. So this is an N well which has been made, and then you put two source and drain P regions. Now if you see here, the operation is very similar. If you apply 5 volts out here, like suppose this is a 5 volt system, so I am explaining it. So this will not be the same always. So if you are using 180 nanometer technology, the power supply will be 1.8. So if you are going to use 45 nanometer, then the power supply is 1 volt. So this is just an illustration. Okay, so suppose this is a 5 volt technology in that case. Okay, so if you are giving an 5 volt here, okay, to the source of the and drain is 0, and you are applying a 5 volt to the gate. Now between the source and the gate, it is 0 volts, right? Because source is also 5 and gate is also 0. So VSG in this case is 0. So that there is no channel cannot be formed here, right? Because you are applying gate 5 volt. This is an N well, right? So it is going to this channel is going to remain N, because it is going to attract electrons only. So this diode will remain reverse biased. Okay, so there is no way a channel will be formed, and there will be no conduction. Now whereas if you give gate is equal to 0 out here, so it is going to attract all the positive ions which are available due to thermal emission in the N well, and also it is going to pull the positive carriers from the adjoining P plus source and drain. So a channel will be formed. So it is a similar operation of that NMOS. Only thing is, now in the source we are giving 5 volt, and in the drain we are grounding it. For NMOS we did the other way around. For the drain we considered an high voltage, and source we were grounding it. Here it is a PMOS. Since it is the positive, the conduction is going to happen using positive ions or holes. We are calling wherever we give the power supply, we are calling it as a source. So that is a nomenclature which we are going to follow. So this is source because it is P type. P type means positive ions are going to flow. So that is the reason this I am calling it as source. And in this case, for the gate, if I give 5 volt, it will be off, and if at the gate I get 0, it is going to switch on. So this is the reverse action as that of an NMOS. Okay, so again the same things remain here also, like an ideally no current should flow, but then in practically a few picoamperes of current will flow. And similarly, when the switch is closed, immediately the drain and source potential will not come to the same value. Current will slowly flow in a restricted manner between the drain and source. And that the source current or the drain current will be dependent on various parameters of the transistor in use. Okay. So now this is how, and finally an NMOS and PMOS is fabricated side by side. So this is a P substrate, you have an NMOS, you have an two N N regions, and you have a gate, so this becomes an NMOS. Whereas for an PMOS, first we in the P substrate we make an N well, and then you put two P regions, so this becomes an PMOS. Okay. So for a PMOS, if you see here, if I have to transmit an 0 here, right, suppose this is VDD here, suppose I have to transmit 1, so I put an now I said to switch on the PMOS, I have to give gate voltage as 0. Now this is 0, this is VDD. Now if you see this, since the carriers is going to be positive ions, now I am going to call this as source. Okay, VDD, wherever I give VDD, because this is how the positive ions are going to move from VDD towards the drain. So that is why I am calling this as source, and I have gate. Now to switch on a PMOS, I need to give a 0 volt here. So I am giving 0 here and VDD here. Now the output voltage, now if you see here, whatever is the drain voltage, so this transistor voltage the PMOS will always remain high, because if you see this is source is VDD, gate is 0 here, right? So VSG in this case is above the threshold voltage, so this will continue to remain on. So this can PMOSFET can pass VDD, so the output voltage will get charged to full VDD, unlike an NMOS. Whereas if I have to transmit an 0, then in that case, if I use a PMOS, if it is 0 here, and then this is the voltage. Suppose we are assuming that this capacitor is already charged to VDD, and then I have put a 0 here, and I am switching on this gate. Okay, by applying A equal to 0 here, then now this capacitor has to get discharged to 0, but it cannot get discharged to 0, because the moment this output voltage reaches VTP, like VTP is nothing but the threshold voltage of this PMOS, okay, then this transistor will get switched off, because for this transistor to remain on, VSG has to be greater than the threshold voltage of the P transistor PMOS. Okay, so that is the reason. So it cannot transmit an 0 properly. So so PMOS has a perfect one, but not 0. Okay. Now another thing which we have to take care in our designs is, like you have an NMOS, whenever you have a body connection also, that is known as the substrate. So this substrate is a P, and this you have N, so you have a diode junction here. You will also have a diode on this side also. So you don't want current to flow from this P to N, forward bias junction. So you have to ensure that this body is connected to the lowest available potential in the circuit. Okay, so you have to take care whenever you are designing a circuit, the body of the NMOS should be connected to the lowest potential available in the circuit. So in digital circuits, we can say it has to be connected to the ground. Same is the case for PMOS. Here the body connection is N well, right? So the N well, you have an P drain and source, so you will find this can get forward biased. Okay, so that should not happen. So for that, the body needs to be, this diode requires to be reverse bias. So the body of all the PMOS should be connected to the highest potential available in the circuit. Okay, so you have to take care of that aspect. Now if you see here, there are two NMOS like this. Okay, so in both the cases, like if you see, this is one is placed, suppose one is placed on top of the other in the schematic, and now you see this body is grounded. You should not connect, short the body and the source here. So this is the common mistake which many of the students do while circuit design. They keep shorting the body and the source. Okay, for this, shorting body and source is okay because the source is grounded, but for this you will see that this body requires to be connected to the lowest possible potential. If you short this, okay, there is a possibility that, and now if suppose this is the second top NMOS, you are doing this short body, short between the source and the body here. Here also you are doing source and the body. So this transistor, there is no issue. For this transistor, suppose this input A is high and B is low. So in that case, what happens is, whatever is VDD is available, that will be available to the source of this transistor. And now if you connect it to the body here, so that VDD will come to the body, whereas for this transistor you have put an onto the body ground, so VDD will get shorted to the ground. So you should not do that. You just have to remember one simple rule, that body of all the NMOS should be connected to the ground. Okay, similarly when I talk about PMOS, all the body of all the PMOS should be connected to VDD. You should not connect the body to the source. Okay, never do that. You can only do that only if the source is connected to VDD. If the source is not connected to VDD, then the body requires to be connected to the VDD. Okay, so that is the general rule. So let me just tell you, it is not that there are certain advanced circuits in which the body is not connected to VDD. In fact, we use the body connection to modulate the VTH and all. But in those cases, like if it is an NMOS, so the NMOS is not directly fabricated onto the P substrate. You make a separate N well. And then inside that N well you make one more P well. So this P well is not actually the substrate. So this is a separate P well exclusively for this NMOS devices. So in this case you can give some voltages to this body also. Okay, because it is not going to affect the other devices, because this is an isolation N well is there. So the next device, the functioning of this device is not going to affect the other device. So this is also possible. Okay, so these kind of things are also possible. Now coming to the last few slides, we are going to now discuss about the power dissipation in CMOS. Okay, so the power in a CMOS circuit basically are of two kinds. One is known as the static power, the other is known as the dynamic power. So the name itself suggests static power means whenever there is no switching of the input and static power means whenever the input is not changing, the input is either 0 or 1, accordingly the output will be either 0 or 1, but still there will be some leakage current in the circuit. That is because we saw that the transistors are not ideal, the MOSFETs, they are not ideal switches, there will be some leakage current. So that is known as static power. Okay, dynamic power is whenever there is input is changing from 0 to 1 and accordingly the output is changing from 1 to 0 or 0 to 1. So within dynamic power there are several kinds of power, switching, short circuit. So we'll see each one of them in brief. Okay, so static loss. So static loss can happen because of several factors. One is the current which is flowing from the gate to the substrate through the insulator. Okay, this is an insulator right in between. So now I said this has been more or less arrested by using high K dielectrics and using a greater thickness of gate oxide. So this leakage current we can neglect as of now. Okay, but then even if when you are not applying any gate voltage, there is some current which is flowing between the drain and the source. So that has become a major issue with the latest technology devices. Okay, now let's see why it has become a major issue. Now if you see, when I say the devices is being scaled, Okay, so what is actually happening is, like if you have an device of initially we had a few micrometers and then we are coming into nanometers. Suppose 180 nanometer technology had a power supply of 1.8 volt. Now 45 nanometer has a supply of just 1 volt, and then you have a 7 nanometer technology and all, which has got even lesser supply voltages of only 0.9 volt. Why is the voltage being scaled? It is because the MOSFET operation remains the same, because along with the device being size being reduced, the voltage also is being reduced, so that the electric field remains same. So and hence the operation of the MOSFET, the concepts remain same. So it is not just if you just keep the voltage high and if you start reducing the size of the transistor, then the electric field will go very high and there could be a rupture of the junction. So along with the voltage, along with this, when we make smaller and smaller sizes devices, the voltage also requires to be brought down, so that the electric field remains constant, and hence there is no device damage, and then it still continues to work like a MOSFET. So along with VDD and feature size, both are reducing. So now what happens if you reduce VDD? If you reduce VDD, okay, if you see the delay, okay, now how is this capacitor being charged? Through the currents. Okay, now the capacitor also here, what is the capacitor? This capacitor, because each gate is going to drive another gate. Okay, so that gate, if you see the input of the into the input of that gate, it is capacitance only, right? Because unlike a BJT, there is no IB here. It will see a capacitor. Then this is going to drive another such inverter. If it is going to drive another CMOS gate, then it will see a capacitor, which is the gate capacitance, the capacitance which is available at the gate of the next stage. So similar also, this drain and this drain terminals also contribute to some capacitance. So this is CL. Now how fast this node will get charged to 1 or how fast this will get discharged to 0 depends on the current which is flowing. And if you see the current equation, so hence you can say the propagation delay is proportional to the CL. If there is large CL, it will take more time, and similarly if you have large current, then the propagation delay will be low. So the CL is reducing as we keep decreasing the feature size, but ID, if you see ID also, ID is dependent on VDD minus VTH, so VDD is also decreasing. So if you don't decrease VTH, then the current will reduce. If the current reduces, then the delays will go high, right? So as you keep decreasing VDD, the VTH, although threshold voltage is also being decreased. And what is threshold voltage? It is that voltage below which the device should be off and above which the device should be on. Now VDD is being reduced, and to keep the current levels high, we are reducing VTH also. That means the threshold voltage, we are slowly getting it close to 0, and hence the leakage current is increasing. So you see how the modern day devices have got a higher threshold leakage current. So that is the reason. The reason is we are forced to reduce VTH because of decrease in VDD. Okay, so that is the thing which you have to take care. Now if you see here, if I make a simple inverter, this is a 45 nanometer inverter response. So if I increase the voltage from 0 to 1, the output would go from 1 to 0. So when the input is 0 here, so this NMOS will be off and PMOS will be on. So the output voltage will be charged to VDD through this PMOS out here, right? So but since this NMOS is off, no current should flow between VDD and ground. Okay, but whereas if you see a BJT circuits and all, continuous current will be flowing there. So as compared to the BJT circuits, this is it has got very less static power consumption. Okay, it is almost negligible. Now so this NMOS should be off, but then it is taking some 15 picoamperes of current in this particular simulation result. Okay, similarly when the VDD is 1, the input is 1, so when it becomes 1, the VDD is also 1, so this PMOS transistor, this is 45 nanometer technology for which the VDD is 1. Okay, now when V in is 1, this is also 1, so this PMOS has to remain off. So whatever NMOS turns on, so whatever is the charge accumulated in the capacitor should get discharged to 0, right? But this is off, so there is no path between VDD and ground. But nevertheless, you will find that 3.5 picoamperes current is flowing from here to here. Okay, so that is why now if you see the width given here, so that is the reason. So if you see here, we are using PMOS to put the take the output to 1, because whenever it is 0, output requires to go to 1. This is an inverter, right? So I am using a PMOS here, so this will go to 1, and PMOS can transmit a perfect 1, so this output voltage also will go to VDD. Whereas when I have to when I give 1 here, okay, this will get switched off, NMOS will be switched on, and NMOS is in perfect 0, so whatever charge is accumulated in the capacitor, that will come to 0. Okay, and then why I am using 2W here and W here, that is because one is to keep this switching somewhere in between. You will find in the ID equation you have something known as mu n and here and mu p here, which determines which is the mobility factor, right? So if you see here, PMOS is much slower than the NMOS, so and also the total current also. So to keep the rise time and fall time, and also this VTC curve in between, so we keep the PMOS to keep make the response similar. We have to use at least twice the width of the NMOS here. So this we will discuss in detail in the next class when we are looking into inverter design. Okay, so that is the reason why I have kept W and 2W in this particular simulation. Okay, now the second kind of loss which happens is short circuit loss. Okay, what is this? So when I give an input voltage, this particular simulation, let's discuss this simulation in terms of 180 nanometer technology. So in 180 nanometer technology, the VTN and VTP is close to 0.6. Okay, the threshold voltages, and VDD is 1.8 volt. Now the input is slowly rising. So the moment it crosses 0.6 volt, this NMOS transistor will be switched on. Okay, whereas this is also switched on, right? This is also remains on, so it will keep increasing, keep increasing, and when the input voltages crosses 1.2 volt, now this is 1.8 volt, when this crosses 1.2 volt, this PMOS will be switched off. So in between these two regions, you will find that both these transistors are on, and there will be a path available from VDD to ground. So whenever an input is making a transition from 0 to 1 or 1 to 0, in that time there will be an spike in current. You will find the current is going high and coming low. Okay, so this will be in few microamperes range. Otherwise you will find it can be in nanoamperes or microamperes. Otherwise you will find that in normal circumstances it is only in picoampere in the static condition. Whenever it is making a transition, both these transistors will be on for a short duration of time. When it is making switching from, when the input will not slowly keep going, right? This is just shown in a slow pattern so that you understand the concepts, but input will make the rise time will be a few nanoseconds only. So even during that few nanoseconds, okay, there will be a spike in current. Okay, that could be in nanoamperes, or even it could be in microamperes range also. So you got to take care of that. Okay, so how to reduce that is, suppose you can use VTH close to VDD by 2. So like technologies like 45 nanometer and all, they give low VTH devices, standard VTH devices, and high VTH devices. So high VTH devices will have VTH close to VDD by 2. So so NMOS will be switched on late and PMOS will be switched off early in that case. So you will have lesser of short circuit currents. But if you are using that, then the propagation delay will be high. But still, if there is some two paths of the circuit, suppose in one path you have 10 gates, and in some other path, and both these paths they end up into some single gate. In the second path you just have 3 gates. So you can afford to use a higher VT in that non-critical path. Non-critical path is that 3 gate path. Okay, because the maximum gates wherever is, whichever path has got the maximum number of gates and largest propagation delay, that is the known as the critical path, because unless that particular, you have to wait for that output to come from there. So in a non-critical path, probably you can use an high VTH device. Okay, so you can do that. Now the third and most important thing loss here is known as switching loss. Okay, so now if you see, if the input, suppose the capacitor initially the output node is 0, input is high, now the input is switching from 1 to 0. So the moment it has switched 1 to 0, the output capacitor needs to be charged to 1 through this PMOS. Okay, so now VDD, through this PMOS current will flow and this capacitor has to get charged to 1. Now if I try to find out what is the energy stored in a capacitor, this is from the basic electrical, if you do an integration of the current and voltage, okay, you will get the energy. So if you do that, you will get a half VDD square CL. Okay, so this is the energy which gets stored into the capacitor. Now if you try to find out what is the energy which is consumed from the source, okay, in this case when we were doing the integration, VC also was an variable, because the as the capacitor, this capacitance voltage 0 to VDD, it is going to raise from 0 to VDD, and that is why this was taken as a VC, right? And then so here in this particular case, if you see, VD is constant, so you just have to integrate the current aspect. So when you do that, you will get VDD square CL. So if VDD square CL is the energy which is taken from the source, and the energy which gets stored in the capacitor is half VDD square, then what about the rest of the energy, half VDD square? That gets dissipated as heat. Okay, so during when the output node is getting charged to 1, you will find half VDD square energy gets dissipated as heat in the PMOS. Okay, similarly, when the input is changing from 0 to 1, the output has to change from 1 to 0. So whatever is the half VDD square CL energy which is stored in the capacitor, that gets discharged through this NMOS. Okay, so this NMOS will pull down this voltage to 0. In that process, half VDD square energy will get dissipated as heat in this NMOS also. So you have to take care of these issues. Now in terms of power, power is energy into this is frequency. Okay, power into energy into frequency, so number of cycles per second. Okay, so if you multiply it with the frequency, you will get frequency to VDD square into CL. So that is the power which is consumed by this inverter. Okay, now if you see, this is a very important equation which we need to remember for CMOS design. So dynamic power is frequency into VDD square into CL. Now if you see here, when we are going from one generation to other, VDD is decreasing, even CL is decreasing. CL is decreasing because the size of the capacitor is decreasing, but still that overall power is increasing because the frequency is increasing. Right? Why is the frequency increasing? Because we are using better algorithms, right? And then better circuits. So hence the frequency is increasing because of architectural optimizations, consumer requirement. Obviously, you and me would want our mobiles or laptops to work faster. So hence we are using higher frequency. Right now we are using few gigahertz frequency, whereas earlier days they used to work in few megahertz. And also the transistors per chip is also increasing exponentially. So because of lithography, like the lithography is the way the small drains and sources are put it into an P substrate, like when we fabricate NMOS. So you can refer to some of the VLSI technology lectures. So you will come to know the lithography. Because of the improvement in lithography, we are able to fabricate more and more transistors in a given silicon area. A multi-layer metallization that we discussed slightly earlier, efficient patterning and routing technique. So these are things which has enabled transistors per chip has gone exponentially, and the frequency has gone, and hence the total dynamic power is increased in these chips. So you understand now why is that we are targeting lesser, and we have to target circuits which consume lesser power. Okay. Now lastly we'll just discuss few figure of merits of a digital circuit. So the first one is noise margin. So if this is, again we will discuss this in detail in the next class, but I'll just cover it in brief here. Now this is the input voltage, this is the output voltage. Now if you see here, till the time the input voltage is almost coming to 0.5 or something, the output is 1. So that means this particular inverter can handle input voltage from 0 to close to 0.45 or something. Okay, so that is that much of noise it can tolerate, right? Similarly, any input voltage from 0.7 here to 1 here, okay, it will consider it as a 1, because the output will be 0, right? For the red line is the output. So this, for this range the output will be 1. So this is known as the noise margin. So this range from 0.7 to 1, okay, or from 0 to say 0.3 or 0.4, whatever. So this 0.4 volt is known as the noise margin low, and this point from 0.6 to 1.4 voltage, this will be considered as noise margin high. Okay, so what is that point where we consider, that is the slope. We take the slope here, wherever the slope is -1, we draw a line here. So this we'll discuss in detail in the next class. So this is known as the noise margin. Okay, noise margin is nothing but the immunity towards noise. Now if you see, this is another problem. As we keep talking about 7 nanometer, the total power supply voltage is reducing, so the noise margin is also very less, right? So this becomes more immune to noise. So there are certain circuits like schematic triggers and all which improves the noise margin, that we'll discuss later. But when we were talking about 180 nanometer technology which we are going to design, it is going to use 1.8 volt. So from 0 to close to 1.9 volt, it will take it as 0. So you will find the noise margins are much better. This is 1 volt for 45 nanometer technology. So you will find the noise margin is pretty poor, right? It is only 0.5 volt. So only that much of noise it can handle. Whereas for an 180 nanometer technology, where the power supply voltage is 1.8, so the mid will be 0.9, so around 0.8 will be the noise margin there. So it is better, right? Propagation delay, like if the input is switching from 0 to high, and this is just an inverter input and output shown here. So these kind of waveforms is applicable to any digital circuit, not only for inverter, it could be an adder, subtractor, whatever it is. So when the input is changing, the output also has to change accordingly, but from the time the input is changing and reaching 50% of its change to the point where the output is reaching 50% of the change, that is known as propagation delays. Okay, now in this case this is known as TP is propagation delay, high to low. When the output is swinging from high to low, it is taking this much of time for it to start falling to reach 50% of its time. So this is known as propagation delay high to low. Similarly, here the input is changing from high to low, the output has to go from 0 to high. Okay, so this is the case of an inverter, a special case of inverter. It is applicable for every circuit. So here it is 0 here. Okay, when the input is changing here, the input is reached 50% at T2, output is reached 50% at T3. So T3 minus T2 is known as the propagation delay low to high, right? So that another way of defining the delays is rise time and fall time. Wherein this is 90% and this is 10%. So time taken for the output voltage to fall from 90% to 10% will be known as the fall time, and the time taken for the output voltage to start from 0. Now if you see here, they need not be same. Okay, when we see the design of various circuits, depending on the sizing of the transistors and things like that, so they need not be the same. Okay, it could be different also. So here this is the rise time. Okay, then there is something known as fan in and fan out. So if you see for a CMOS design, the number of it's for an inverter, fan out means the number of inverters you are connecting at the output. Okay, that becomes, so you can have an n number of one inverter can theoretically drive infinite number of gates. Okay, because in the static condition there is no current which is flowing from here to here. These are all gate capacitance. So unlike in a BJT, you can't do that. In a BJT, if you keep driving one gate, BJT based logic families, if you keep increasing the fan out, this output voltage available will keep decreasing it. Okay, and then finally it will fall below the prescribed levels. In CMOS that doesn't happen. You can keep increasing the number of gates to infinite. Only thing is, as you keep increasing the number of gates, the net capacitance at this node increases, so the response will be slower, so there will be greater propagation delays. Okay, so that is the only problem. So generally when we design a circuits and all, we design when we are reporting a new circuit, we will take a fan out of 4 and describe the performance. Okay, so for a fan out of 4, what will be the performance? Okay, so a fan in is nothing but the number of gates which it can take as an input. Okay, so that is fan in. And this power and energy, we already discussed a lot about these things. So these are another, it's a very important figure of merit, because power consumption determines how much heat is dissipated in the circuit, what should be the power supply capacity, like the metal lines which is getting the VDD to the devices. Okay, the size of that also depends on the power which is being consumed by the circuit. So average power dissipation. So this we have already discussed. So this is one of the important figure of merit. And finally, power delay product, right? So if you just mention, okay, this circuit is operating much faster, okay, or we say this circuit is consumes lesser power. Okay, that doesn't give a good picture, a complete picture, because if you see the dynamic power equation, it is frequency VDD square and CL. So in a circuit, if you just drop the VDD, your dynamic power will reduce, right? But at what cost? It will increase the delay. If you reduce the VDD, you will find that delay is increased, right? Similarly, if you want to reduce the delay, you can increase VDD, but that will increase the power, right? So whenever you are comparing two circuits, you have something known as power delay product. That is, you multiply the power and the delay, and then you get a figure of merit. Okay, and then between two circuits, if one circuit has got a better power delay product, then you can say that circuit is better. Okay, just because always they can be compromised. One of them can be compromised to improve the performance. Okay, that means with higher power you can get better, lesser propagation delay, and with greater delay you can get lesser power. Okay, so you have a figure of merit known as power delay product, which is the product of power and the delay. So that is what we generally is used to compare the performance of two circuits. Okay, and now with this we end this theory part here. Now I will show you the demonstration of how to install TSMC 180 nanometer technology files in LT Spice. Thanks a lot.